Hello, welcome to the Lumension video series on Defense in Depth. In this video, we will focus on mitigating threats to end-user PCs, as well as servers, through a layer of defense known as Advanced Memory Protection. To understand this defense, we need to understand the nature of the attack. So we'll first look at how an attacker establishes a foothold in a victim system through what is known as an exploit, in particular, a memory exploit. We'll then discuss the steps an attacker uses to climb further and further into a computing system. With that basis of understanding, we'll look at several possible layers of defense that an endpoint can utilize to thwart an attack. And finally, we'll conclude with a demonstration of one of the layers of defense, Advanced Memory Protection. So there are certainly many ways an adversary can seek and obtain access to a computer system, to obtain information to breach confidentiality, or to disrupt systems to affect availability, or to alter data to compromise integrity. We're focused here on attacks that target software, Windows software in particular, whether that be the operating system itself or software applications running within the Windows family. Newsflash, software applications have bugs. In particular, programs may have flaws in how they store data, manipulate data, or verify the data's validity. These vulnerabilities are typically the result of something being overlooked in the design or development of the software. By simply inputting too much data, or data crafted in a particular manner, an attacker can disrupt the normal flow of the software and potentially trick the system into executing an initial set of instructions. This is known as a memory exploit. Once an attacker has successfully gained a foothold in memory, it's common for them to try to load additional payloads into memory or even to install more permanent payloads to disk. There are many different types of memory exploits. When an attack inputs too much data and a storage area is overrun, the exploit is simply known as a buffer overflow or buffer overrun. You may hear more specific terms relating to the particular area of memory that was overrun, such as the stack, to create a stack overflow, and stacks are typically used for the management of more dynamic data, or a heap overflow, where heaps manage more static data. Whatever we call them, buffer overflows are a big problem. Over the past 25 years, if we look at National Vulnerability Database data, buffer overflows have been the most common vulnerability at 14%. During the same time frame, they represent a disproportionate percentage of high criticality vulnerabilities at 23%. Why are these so common? Much of it may lie in the underlying languages, such as C and C++, which provide the programmer fantastic memory management capabilities. But, as with great power comes great responsibility, and as the complexity of software increases, there is increasing room for overlooking some aspect of memory management. Having looked at the attacker's initial foothold, the exploit, let's look at a more complete sequence of an attack, in this case establishing a more permanent presence of malware on an endpoint. On the lower left is the vulnerable application. Because the attacker or attacking software has to interact with the application, it may be easiest to think of this application as a web browser, as a browser readily receives input from a number of sources. This application could just as easily be an email client, a piece of document processing software such as a PDF reader, or a multimedia player. Certainly, in discussing depth and defense, there are layers of defense which may come into play here. A layer of defense such as URL filtering may help. However, the statistics on malicious URLs are staggering, and it's not always possible for URL filtering to know of all malicious malware sites. So my browser, my vulnerable application, visits a malicious site, which provides an attacker an opportunity to provide something on the page which overflows or improperly accesses the browser's storage. This may simply cause the browser to halt. However, often through a great deal of craftiness and cleverness, the attacker is often able to place data somewhere in memory that it shouldn't be. And the attacker has crafted the data as to be a small set of initial instructions known as shellcode. This memory, which was originally compromised, typically does not offer enough room to do much, so the attacker must branch out. This is commonly done by a process known as memory injection. Memory injection often takes advantage of known software on the system, and as the wolf in the sheep's clothing indicates, malicious code may be injected into existing software which is known to be harmless. However, the attacker's presence at this point is only in memory. It may, and typically does, have significant capabilities to access data on the system. However, it is not permanent. If the machine were shut down and rebooted, the attacker's presence would be lost, and the attacker would have to again begin work to establish a presence. To avoid this, an attack may write to disk a more permanent malware executable which would survive a reboot. Having looked at the attack process, let's look at the possible layers of defense to stop the attack. Along the way, we're going to use a rather imperfect analogy, that of a home burglary. The first steps for either an attack or a theft are not shown. One of the first things to do would be to select a desirable target, and the second would be casing the joint, looking for vulnerabilities and when and how to possibly act. Once a target has been identified, for an attacker, the next step is then to attempt to exploit the existing or known vulnerability. At Lumension, we believe it's fundamental to security to eliminate the known vulnerabilities up front. This layer of defense is provided by the Lumension Patch and Remediation Module, or LPR. In terms of the home burglary analogy, a vulnerability might be thought of as an unlocked front door, and the patch which eliminates this is locking the front door. However, if the vulnerability exists, there is an opportunity to launch the exploit. From the defensive perspective, there's still ample opportunity to block further malicious activity. In terms of the burglary analogy, we might have an armed alarm system which has a front door sensor. If opening the door caused an immediate response preventing the theft, then that would be similar to the protection layer labeled as OS native protection. For the computer attack, one of the primary memory protection technologies is called DEP, or Data Execution Prevention, and it requires that instructions only execute from specific portions of memory. This blocks attacks where memory exploits overflow memory with instructions in non-executable areas. Though a good layer of defense, one thing to bear in mind is that attackers always look to develop techniques to bypass defenses, and techniques have been developed to bypass DEP as well as the technology known as ASLR. ASLR is address space layout randomization, and it does not so much stop an exploit as make progressing into the system more difficult. In terms of the burglary analogy, it is somewhat akin to shutting off the lights or turning off power to the house to make it more difficult to find things of use, like say the staircase. With ASLR, what is more difficult to find are the existing software executables in the memory space. Both ASLR and DEP in modern applications and Windows OSs are implemented as the programs are built at so-called compile time. Microsoft also provides a potential layer of protection in something known as the Enhanced Mitigation Experience Toolkit, or EMIT. EMIT allows ASLR and DEP to be enabled for older applications which did not originally support these technologies, and perhaps more importantly provides an additional set of exploit mitigation technologies. We will not cover these in detail here. We'll just note that one of the technologies by its very name conveys its role in helping to protect memory. On the screen we see the acronym SEHOP. SEH stands for Structured Exception Handler, which we will not cover in this video. But note that the final two letters, OP, stand for Overwrite Protection, clearly indicating some type of overflow prevention present in the technology. As these particular protections are very low level and often tied to the operating system, Lumension does not provide these. Lumension, however, may be able to help facilitate the deployment of these technologies through a software module known as the Lumension Content Wizard. Going back to our home burglary analogy, at this point, the thief has unlocked the door and bypassed the front door alarm sensor and bypassed ASLR by bringing a flashlight, and now seeks access to the items of real value within the home. And let us suppose that there is a safe within the house. Memory injection protection may be thought of as a separate alarm system for the safe, detecting any untoward activities that reach this resource located further within the house. Remember that memory injection is the act of expanding malicious capabilities into larger segments of memory. If the injection utilizes pre-existing system calls to load the larger executable code, then this activity may be typically detected by a defense layer known as application control. As application control is tasked with monitoring the loading of executables, or more properly files with a PE or portable executable header, application control has potential system visibility to this type of injection, known as SCAPE-JT. A much more difficult injection to detect is known as reflective DLL injection, which loads additional malicious code through a reflective or self-loading process. Detecting this reflective injection must be done by more intricate system monitoring. Detecting such reflective DLL injection is performed by Lumension's Advanced Memory Protection. Advanced Memory Protection is offered as a component of the Lumension Application Control module. From there, the attacker might wish to establish a more permanent presence, which would be malware written to disk, which might be detectable by application control or antivirus. Completing the burglary analogy, what would a permanent presence be? Perhaps this would be as simple as a piece of tape left over a lock to allow re-entry, or perhaps more in line, a listening device or video recorder, complete with RF transmitters to continuously access information within the home.